My name is Rishi Bhardwaj. I work here at Nutanix. And today I'm going to be talking about the Nutanix Metadata Store. So Nutanix introduced its first hyper-converged platform back in 2011. And the storage fabric inside Nutanix, which is called the Acropolis Distributed Storage Fabric, or ADSF, supports various storage protocols. We do iSCSI block storage, and we also do NFS and SMB file system as well. And on top of that, we support multiple features like snapshots, deduplication, erasure coding, to name a few. And needless to say, when you support such features, the metadata requirements for storing your data becomes more and more involved, more complicated. The metadata grows quite a lot. In which respect, the metadata subsystem of Nutanix is quite a piece of engineering in itself. And I'm going to talk about that metadata store of Nutanix, which is known as Medusa Store. So we are talking about Medusa Store, the Nutanix metadata store. Let's take a step back and ask what is required of the Nutanix Medusa Store, or why is it the way it is. So the ADSF does not require or does not use a distributed lock manager for synchronizing data and metadata access in its distributed systems architecture. So ADSF has a coarse vdisk level lock, a vdisk lock at the top that synchronizes any writes happening to a vdisk. So all the writes for a vdisk will only happen or go through a node which has acquired the vdisk lock at the top. So any changes to your vdisk will only be affected by the node that holds that vdisk level lock. So that's a coarse lock for the whole vdisk, and that sort of synchronizes all writes happening to that vdisk. But the metadata for vdisks is more fine-grained. It's not as coarse. As we discussed before, the data extents can be big, can be small, can be snapshotted, deduped, et cetera. And this metadata for vdisks may be shared across different vdisks. So when the metadata is shared across different vdisks, multiple nodes may try to concurrently access that metadata. And we don't have any locks when such a case happens, when multiple nodes may try to access the shared metadata for vdisks. So now you ask what happens when two writes from two different nodes try to change the same metadata for different vdisks. Well, the ADSF assumes that the metadata store has atomic compare and swap primitive. So the atomic compare and swap or atomic CAS primitive makes sure that if two writes concurrently try to change the same metadata, only one of them succeeds and the other fails. And through atomic CAS, ADSF synchronizes concurrent writes to shared metadata. So let me mention the salient features of Medusa Store. As we discussed before, Medusa Store offers atomic compare and swap primitive. And we are able to do that in a distributed storage environment through an efficient implementation of Paxos consensus protocol. Paxos is a distributed consensus protocol, which allows you to choose one value when there are multiple values being written. You can get one of them chosen. And through that, we are able to provide atomic compare and swap primitive. The other thing that Medusa Store does and provides is performance. A lot of implementations out there cut corners when they are implementing Paxos, and they cut corners as far as performance is concerned in the name of simplicity, because Paxos can be a bit tricky to implement. Not at Nutanix. We ensured that our Paxos implementation is efficient in the size and the number of messages that we send for the Paxos protocol, such that it's very good for performance. And we can do tens of thousands of writes per second per node for Paxos writes itself. So the third thing that Medusa Store provides, which is very critical for ADSF, is strong consistency. A lot of distributed key value stores out there provide something which is called eventual consistency, something which will not fly for ADSF. ADSF provides NFS file storage or iSCSI block storage. For such a system, our metadata can't flip-flop, or it can't be eventually consistent. It has to be strongly consistent. The view it provides, the ADSF has to be as consistent as it can be. And for that, we provide these 3 consistency guarantees, which are very important for ADSF, which is read after write. If you write something, you will get that when you read it. Write after write, which is simple, that once you overwrite something, the old value is gone, the new one is seen. And the more tricky consistency guarantee is read after read consistency. Tricky to implement. I would highly recommend reading the blog for what is read after read consistency. In some sense, if you read the 2 values without a write in between, you should see the same value, no matter what. Fourth and final thing that's very critical, again, for our system is reliability and availability. The nodes in Nutanix ADSF can go up and down, and they can go up and down in any order. But until quorum replica nodes are up, which means for RF3, if there is only 1 node which is down, and for RF5, there are 2 nodes down, we are up and available. That means fault tolerance 1 or fault tolerance 2, you can take 1 node failure with fault tolerance 1, and with fault tolerance 2, you can take 2 node failures. And the nodes can be up and down in any order, doesn't matter. Till the quorum nodes are up, the Medusa Store is up and working. This allows us to support features like rolling upgrades in Nutanix, and in general provides the invisible infrastructure where the customer can relax and not worry about its infrastructure going up and down. Thank you.